Hi everybody, welcome to part 2 of the section 4.2 in the textbook. So remember, this is the section unit circle definitions of sine, cosine, and tangent. And in part 1 of the video, we defined sine, cosine, and tangent using the unit circle. We found their domains and ranges. We sketched graphs of those functions. I talked about the even-odd identities. We'll use those shortly. We talked about the Pythagorean identity and did a few examples. And I left off with example 2. Now, what I'm going to start doing here is, now we'd actually like to be able to compute these functions for specific angles. Okay, now what I'm going to do is I'm going to start at the very bottom of this handout. You're going to notice that I have a table down here. And my table should have probably had an extra row, or I should have labeled the top row. So the top row are the special angles in the first quadrant. So for anywhere between a 0 revolution or a quarter revolution, and the special angles are 0, pi over 6, pi over 4, pi over 3, and pi over 2. It actually turns out that if you know sine, cosine, and tangent for these special angles, you can actually use the even-odd identities, and you can use what you know about coterminal identities to find sine, cosine, and tangent for the rest of the special angles between 0 and 2 pi. Okay, and we'll do a few examples of those as well. Now I'm going to start with, I think 0 and pi over 2 are actually quite easy. In fact, we already know those. For a 0 degree angle, we can find sine, cosine, and tangent using the unit circle. Same is true for pi over 2. But I'm going to go back now and find sine, cosine, and tangent for pi over 6, pi over 4, and pi over 3, starting with pi over 4. So we're going to use the Pythagorean identity to find sine of pi over 4 and cosine of pi over 4. Okay, now, one thing I'm going to just convince all of you first before I do this is looking at the unit circle. I'm just going to try my best to draw. I can't draw a circle without doing tick marks. So here's my unit circle in the XY plane. And pi over 4 is actually right in the middle of 0 and pi over 2. So if I take my angle, if I form my angle starting with my initial side in standard position, pi over 4 is going to split quadrant 1 directly in the middle. And here I get my point. So here's the angle pi over 4. The coordinates of this point are, we know the x coordinate would be cosine of pi over 4. The y coordinate would be sine of pi over 4. Okay. Now, one thing I maybe forgot to mention in the first video is that you'll notice that I haven't really talked about degrees at all. The definitions of sine, cosine, and tangent, strictly speaking for right now, we're really only going to be thinking about angles and radians, although you could convert your radians to degrees. But I'll say more about that later. Now, since the angle splits the first quadrant directly in the middle, it is a fact, or you can maybe kind of convince yourself, or at least just believe this is intuitively true, that the x and y coordinates of that point on the unit circle are the same. Okay, so it is true that sine of pi over 4 is the same as cosine of pi over 4. Okay. So I'm going to start with the Pythagorean identity now, okay? And we're going to plug pi over 4 in for the angle. So we know sine squared of pi over 4 plus cosine squared of pi over 4 is equal to positive 1. I'm going to find sine pi over 4 first. Since sine of pi over 4 and cosine pi over 4 are the same, I can rewrite this as sine squared pi over 4 plus another sine squared pi over 4, and this has to equal positive 1. the left-hand side, it's just like x plus x is 2x. Sine squared pi over 4 plus sine squared pi over 4 is 2 sine squared pi over 4, and we know that equals positive 1. I am going to divide both sides by 2. Sine squared pi over 4 is going to equal 1/2. And taking a square root on both sides, sine of pi over 4, technically it's plus or minus 1 over the square root of 2, but since we're in the first quadrant and sine is the y-coordinate, sine has to be positive valued. So we actually end up getting the square root of 1/2. And you can take the square root of the numerator and the denominator. So sine of pi over 4, which is also equal to cosine of pi over 4, we now know is 1 over the square root of 2. Or, if you like, you could rationalize the denominator by multiplying top and bottom by square root of 2. I'll let you think about how to simplify that. Some people like to write this as root 2 over 2. Some people like to rationalize the denominator. I, most of the time, just use 1 over the square root of 2. But there you have it. So now there's our first special angle, pi over 4. And now we know that sine of pi over 4 and cosine pi over 4 are both 1 over the square root of 2. Okay. All right, so that's awesome. Next, we're going to handle pi over 6 and pi over 3. Okay, so what we're going to do next is I'm going to find sine theta, cosine theta, and tangent theta for pi over 6 and pi over 3. And we're actually going to use this using what are called equilateral triangles of length 1. Okay, so let me show you how this works. Let me give myself some room here to do this. So we're going to find cosine pi over 3 and sine pi over 6 using an equilateral triangle. I'll show you how. Okay, so we're going to find sine theta, cosine theta, and tangent theta for the angles pi over 6 and pi over 3. Now, I'm going to switch this up a little bit. I'll have to repost or just pay very close attention. I'd kind of changed the wording in this problem, so if I haven't done that yet on the handout, just ignore that until I update an updated handout. So I'm going to find cosine pi over 6 and sine pi over 6 using an equilateral triangle with sides of length 1. Now, what do I mean by using an equilateral triangle? So, first what we're going to do is let's draw a unit circle. Okay. Imagine the center being the origin. If we're going to form an angle, let's do it with the initial side in standard position. Now, pi over 6, right, if I'll just draw this vertical line through and the horizontal line through, pi over 6 is obviously greater than 0 and less than pi over 2. So this is an angle of pi over 6, and the coordinates of this point up here are cosine pi over 6 and sine pi over 6. Okay, now what I can do is, it's kind of hard to see let me actually make some room inside this thing right here. Let me relabel this as theta, and what I'm going to do is I'm going to drop a perpendicular from that point down to the x-axis to create a right triangle for now. Okay, now I'm going to extract this triangle out of the picture. And let's see. So here's my triangle. The angle right here is pi over 6. Now you can do a conversion. It turns out that if you convert pi over 6 to degrees, pi over 6 is a 30-degree angle. And it turns out that pi over 3 is a 60-degree angle, just to help us. Now, it turns out that I'm just going to call the base of this triangle A, or and let's call the height B. but we do know that really the base of the triangle is just the x-coordinate of the point on the unit circle. So we know that A is cosine pi over 6. And the height of the triangle B is just the y-coordinate of the point on the unit circle. That would be sine of pi over 6. Okay. Now here's the trick. What we're going to do is we're going to draw a copy of this triangle. Okay. And keep in mind that I guess the hypotenuse of this triangle had to be positive 1 because we were on the unit circle. And now I'm just going to draw the entire triangle just as a single one. There we go. Okay. So now, since I guess, let me just draw this through just to illustrate this. Since I just drew a copy of the top triangle below it, I basically now have a triangle where one side is length 2b and the other two sides have length 1. But notice one thing I've done is since this angle and this angle are both pi over 6 or 30 degrees, this entire inside angle is really 60 degrees. Okay. And it is true that the 3 inside of just the single right triangle on the top, all 3 angles have to add up to 180 degrees. And for that reason, this top angle would also be 60 degrees and this bottom angle would also be 60 degrees. Okay, so now this is what is called an equilateral triangle. And the good news here is that all 3 sides have to have the same value or the same length. So anytime you have a triangle where all 3 of the angles are the same, they're all 60 degrees, turns out all 3 of the sides have to be the same length. So that means that 2b has to equal positive 1, or in this case, b has to equal 1/2. Okay, so now what I know is, going back to the bottom left, since I know that b is sine of pi over 6, now I know that sine of pi over 6 is 1/2. Okay. So I extracted a triangle out of my unit circle, I reflected it over itself to draw a second copy. That formed an equilateral triangle where all angles are pi over 3 or 60 degrees, meaning all 3 of the outer sides have the same length. Since we knew the hypotenuse of the top triangle was 1, the hypotenuse of the bottom triangle has to be 1, and the third side, which we now know is length 2b, also has to be positive 1. Solving for b, you get 1/2. That gives me sine of pi over 6. Okay. So let me write that on the top here just so we have it. Sine of pi over 6 is equal to 1/2. Now, I could either use the Pythagorean identity to find cosine pi over 6, or I can even just go back to my original right triangle. Okay, so here's what I'm going to do. I'm actually going to get rid of my second copy over here on the left. I'm going to erase all this stuff for now. And we know that now the height of this triangle is 1/2. And to solve for a, which is cosine pi over 6, I'm just going to use the Pythagorean theorem. Okay, sorry, I got distracted with a call there. So what I'm saying is, now that I know that the height of this triangle, which is also sine of pi over 6, is 1/2, now I'll just kind of get rid of that second copy that I drew. And now I just need to find the base of that triangle to get cosine of pi over 6. And I'm just going to use the Pythagorean theorem. So now I know that a squared plus 1/2 squared has to equal the hypotenuse squared. Okay, 1 or 1 squared. Now what you can do is 1/2 squared is 1/4. You can subtract 1/4 from both sides to get a squared equals 3/4. and I'll take the square root of both sides. The right-hand side ends up being the square root of 3/4, which is the square root of 3 over the square root of 4, which is 2. And there we go. Now we have cosine pi over 6. We know that was a. That's the square root of 3 over 2. Okay, so now I have sine of pi over 6, and I have cosine pi over 6. Okay. And technically I could find tangent pi over 6 because tangent is just sine divided by cosine. But we'll wait till part C to do that. Okay, so now what I'm going to do is now we've already done a lot of this work. So I'm going to come down to part B, and I'm just going to repeat part A using pi over 3, and I'll use the equilateral triangle thing again. So now I'll just draw a unit circle. Here's the vertical axis, here's the horizontal axis. And again, I'll just draw an angle in standard position that has value pi over 3. So this angle is pi over 3. And you can just drop that down again and pull out that, you can drop down what's called a perpendicular. So from the point at the top of the unit circle here, I'm just dropping a perpendicular line down to the x-axis, and I'll pull out this triangle. Okay, it's a right triangle. The angle down here would be your pi over 3, or 60 degrees. The base of this triangle is going to be cosine of pi over 3, or cosine of 60 degrees, and the height is going to be sine of pi over 3. Okay. Now what we're going to do is, the way I'm going to draw the copy is going to be a little bit different this time. I'm actually going to redraw that triangle, but this time I'm going to draw the copy to the right side of this thing. Okay. And again, since the hypotenuse of the triangle was 1, these two sides are positive 1. The base here would be 2 times cosine of pi over 3. Since I've really just I've doubled cosine pi over 3, so now I have 2 cosine pi over 3. And we have now formed, again, an equilateral triangle because the angles in both the bottom left and right corners are 60 degrees. The top angle in our triangle on the left, this angle right here, was 30 degrees. So if we double it, we also get 60 degrees for all these angles. Since we have an equilateral triangle, all 3 sides are the same. So it's true that 2 cosine pi over 3 is equal to positive 1. So cosine pi over 3 is equal to 1/2. And I'll just, give you the shortcut here is using the Pythagorean theorem or Pythagorean identity. It turns out that sine of pi over 3 is square root of 3 over 2. Okay. So that's how I get sine and cosine of both pi over 6 and pi over 3. So now for part C, here's what I have. I want to find tangent pi over 3 and tangent pi over 6. So what we know so far is sine of pi over 6 was 1/2. Cosine of pi over 6 was root 3 over 2. Sine of pi over 3, you'll notice that these values just swap each other. So sine of pi over 3 is root 3 over 2. And cosine of pi over 3 is 1/2. So now if I want to do tangent of pi over 6, that's sine divided by cosine. So I get 1/2 divided by root 3 over 2. Dividing by a fraction is the same as multiplying by the reciprocal. So I'll just cross off the root 3 over 2 and instead multiply by 2 over root 3. And the result becomes the 2's cancel and you get 1 over the square root of 3. So there's your tangent pi over 6. Tangent pi over 3 would be sine of pi over 3 divided by cosine pi over 3, which is root 3 over 2 divided by 1/2. Dividing by 1/2 is the same as multiplying by the reciprocal, positive 2, and you just get the square root of 3. Okay. Now I'm going to summarize all of this in the table on the next page. So here is your table of values for sine, cosine, and tangent in the first quadrant. And then I just have a couple more examples to do before I'm done. So again, the first row represents the angles theta. Okay. Now, if you're on the unit circle again, you've got these 4 points with coordinates 1, 0, 0, 1. The leftmost point has coordinates -1, 0, and the bottom point has coordinates 0, -1. So sine of 0 would be a 0-degree angle pointing to the rightmost point on the unit circle. Sine is the y-coordinate. We know sine of 0 is 0. Okay, cosine of 0 is +1, and tangent is sine over cosine, which would give you 0. Let me create some rows and columns here just so I have some things to fill in. Now I'll do sine of pi over 2. Pi over 2 points to the top of the unit circle. Sine is the y-coordinate of 1. Cosine is the x-coordinate of 0. And we know that tangent is undefined, or does not exist at pi over 2. Okay, 1 divided by 0 is undefined. We know sine and cosine are both 1 over square root of 2 at pi over 4. And tangent is sine over cosine. You get +1. From the previous example, sine of pi over 6 is 1/2. Cosine pi over 6 is √3 over 2. Tangent is sine over cosine. We got 1 over the square root of 3. Sine of pi, and for the nice way to remember this is for pi over 3, the values of sine and cosine from pi over 6 swap each other. So sine of pi over 3 is √3 over 2. Cosine pi over 3 is 1/2. Tangent is sine over cosine, and we got square root of 3. So there's all the values of sine, cosine, and tangent for special angles between 0 and pi over 2. And I really just want to do a couple more examples. And I want to use this table, and I want to use the even and odd identities, and I want to use kind of symmetries to find sine and cosine and tangent of some of the angles on some of the angles between 0 and 2 pi that are not in the first quadrant. So it turns out that if you just remember the special values of the trig functions from 0 to pi over 2, you can kind of use the even-odd identities, you can use coterminal angles, and you can use symmetry to find some of the other special angles. So for example, let's say I want to find, I'll do this in purple on the left. Oops. So here's an example. What if I want to find, say, sine of, let's say, 5 pi over 6. Or let me write that up here. Sine of 5 pi over 6. Okay, how are we going to do this? It turns out that the value of sine of 5 pi over 6 can be gotten from the value of sine of pi over 6. So what we can do is if you draw a unit circle, okay, and with an x-axis and a y-axis. Now 5 pi over 6 is in the second quadrant. So if I take my angle in standard position, right here is, let's just say that this is where 5 pi over 6 is. Now, this little angle right here, okay, since the original angle I was given was 5 pi over 6, and the bigger angle and the smaller angle make up pi, the smaller angle right here has to be pi over 6. Okay. Now, sine of 5 pi over 6 would be the y-coordinate of that point over here. So sine of 5 pi over 6 is the y-coordinate of that point. Now, what I'm going to do here is I'm just going to reflect the terminal side back over into the first quadrant. This little angle right here is also pi over 6, and we know the coordinates of this point are cosine pi over 6 would be the x-coordinate, root 3 over 2. Sine pi over 6 would be the y-coordinate, which is 1/2. Notice that the point corresponding to the 5 pi over 6 angle is just a reflection of the point corresponding to a pi over 6 angle. So what are the coordinates of the what would the coordinates be of the point corresponding to the angle of 5 pi over 6? Both those points have the same height. So sine of 5 pi over 6 actually has to be 1/2, and I'll just show you what cosine 5 pi over 6 is anyways. If you reflect the point with coordinates root 3 over 2 1/2 over the y-axis, the x-coordinate is just going to change by sine. Okay, so the point that corresponds to 5 pi over 6 is just a reflection of the point corresponding to pi over 6 over the y-axis. So you're just changing the sign of the x-coordinate. For that reason, sine of 5 pi over 6 is minus root 3 over 2. Okay. So there's one example of how to get, say, sine of an angle like 5 pi over 6. Okay, so how about I give you one more example? So what if I say find cosine of negative 7 pi over 4? Okay, there's a couple different ways to do this. Anytime you, actually, you know what? Let me make this a little more interesting. Let me say like minus 13 pi over 4. Okay. So there's now a couple ways to do this. One is to first notice that cosine is an even function. So we talked about this earlier. So it ends up being true that cosine of negative 13 pi over 4 is the same as cosine of positive 13 pi over 4. Okay. Now, the angle 13 pi over 4 is not between 0 and 2 pi. So what I'm going to do is, one thing that ends up being true is that sine and cosine have the same value as, for two different angles, sine and cosine have the same value as long as those angles are coterminal, right? Coterminal angles point to the same point on the unit circle. So coterminal angles point to a point on the unit circle with the same coordinates. So one thing you could do is you could subtract 2 pi from that angle, and you would get the same value. Okay, 13 pi over 4 and 13 pi over 4 minus 2 pi both have the same, they're coterminal. Both those angles have the same terminal side, so the corresponding point on the unit circle has the same coordinates. 13 pi over 4 minus 2 pi is, let's see, that's 13 pi over 4 minus 8 pi over 4. You're going to end up getting 5 pi over 4. Okay. All right, so how are we going to do this? Where is 5 pi over 4? Well, 5/4 is between 1 and 3/2. Okay, so I'm going to come over here to the right. So I want you to notice that, let's see, I want you to notice that 5 pi over 4 is bigger than pi, but less than 3 pi over 2. And that's because 5/4 is less than 3/2. 5/4 is 1.25, 3/2 is 1.5. So that means the angle 5 pi over 4 is in quadrant 3. So let me draw a picture of the unit circle. I know my angle now, 5 pi over 4, is in this quadrant. Oops. So there's my 5 pi over 4 angle. Okay. Now, we're going to use some symmetry here. Okay, now first thing I want you to notice is if halfway around the circle is pi, and we're going 5 pi over 4 to get to the angle, this small angle right here has to be pi over 4. Now what I'm going to do is, let me get rid of my 5 pi over 4. I am going to just reflect the terminal side over the y-axis once, and then I'm going to reflect that over the x-axis once. So now I have a, or actually better yet, why don't I just do this? Why don't I just draw the terminal side of the angle pi over 4? That's parallel to the terminal side of the angle 5 pi over 4. That was this angle over here in purple. Okay, now we know the coordinates of the points here on the unit circle for an angle of pi over 4 because the x-coordinate is cosine pi over 4, that's 1 over root 2. And the y-coordinate would be sine of pi over 4, which is also 1 over root 2. So, by using reflections, reflecting over the y-axis and then reflecting over the x-axis, what that does is it changes the sign on both those coordinates. So, for the angle 5 pi over 4, the terminal side of that angle now is going to point to the point on the unit circle with coordinates minus 1 over root 2 minus 1 over root 2. Okay, so cosine of 5 pi over 4 is the same as sine of 5 pi over 4. They're both minus 1 over root 2. So coming back over to the left, now I know that cosine of 5 pi over 4 is minus 1 over root 2. So that gives me the original answer. I know now that cosine minus 13 pi over 4 is negative 1 over root 2. Okay, so it's a little tricky to get used to this at first. I used quite a few identities here. I used the fact that cosine's an even function, so cosine of a negative angle is the same as cosine of the same angle by eliminating the sign. In the second step right here, I use the fact that sine and cosine have the same value for coterminal angles, so I subtracted 2 pi, and the result would be equal to cosine of 5 pi over 4. Once you get an angle between 0 and 2 pi, you can kind of just draw pictures in your unit circle and use what you know about the angles between 0 and pi over 2 in symmetry to find the coordinates on the unit circle corresponding to the angle of 5 pi over 4. And in this case, the x-coordinate of that point is the value of cosine 5 pi over 4, and hence the value of cosine negative 13 pi over 4. So play around with that. I'm sure a lot of people have questions. Make sure you ask me in class. We can do plenty of examples. One of your homework assignments is actually to fill out the entire unit, the coordinates of the unit circle for all the special angles between 0 and 2 pi. And you can again use the symmetries. So get working on the homework. If anybody has questions, let me know. Thanks for tuning in. Have a good one.